Swayam Prabha. Digital India. Educated India.
Welcome. So we are in module 3 and we are in last lecture of module 3. So here what I plan is the quadratic shape functions. First I will show you how to derive quadratic shape functions, and then again we'll discuss in the in connection with axial bar problem, and then then we will discuss the eigenvalue problem that we have discussed in the previous lectures, that is how to find out natural frequency and mode shape of a axial bar. So now to start with axial bar problem, means to start with quadratic shape functions, we have already seen the linear shape functions or linear Lagrange polynomial. So what is the Lagrange polynomial? Lagrange polynomial is this that we have seen in the previous class. So Lj basically is this is a product sign, Lagrange interpolating polynomial. Now that is equals to k equals to 1 to n, where n is the number of points, and then k not equal to j, that is x minus xk divided by xj minus xk. So here it is assumed that each point is a distinctive point, that means no two points are same. And so for one node two node axial element, so we have found out how to do this. So this is node 1 and node 2 if the coordinate is x1 and x2. So L1 is basically x minus x2 by x1 minus x2, and then L2 is x minus x1 by x2 minus x1. So this is the Lagrange polynomial, which is a linear polynomial, obviously linear Lagrange polynomial. So it is interpolating polynomial, and then if I change it to the this local coordinate system, then this becomes simply this, that if this is x1 becomes 0, that is 0 to Le, if it is length is Le, then this polynomial is essentially our means if I substitute x1 equals to 0 and x2 is Le, then this polynomial will looks like something like this, is 1 minus x by Le, and L2 is x by Le. Now this is our shape functions for the linear bar element or two noded bar element, for which we approximate using finite using our field variable ux within an element. We approximate like this, that is 1 minus x by Le. So this is in bar quantity because I am just discussing it over x. So now this is x by Le u2, so you can put bar on it because we are discussing in the local coordinate system. So now this is the shape function, and for which we have found out the stiffness matrix in the previous class. So stiffness matrix for this is something like this, that is AE by LE 1 minus 1 minus 1 1. So now in case of a quadratic polynomial or quadratic Lagrange polynomial, we how to do this, that we can find out. So we can find out in case of a quadratic polynomial, obviously we need more points. So at least we need 3 points. So 1, 2 and 3. So if I choose x1, x2 and x3 are my coordinates, then I can construct its Lagrange polynomial. And then similarly in the local coordinate system I can find it out. Now instead of that, we can also do it in this way, that if I choose that my ux is a general quadratic polynomial, that is a plus bx plus cx squared, then with this, that is u1, u2 and u3, if it is displacement for these 3 nodes, then I can choose this a plus bx1 plus cx1 square, and then u2 a plus bx2 plus cx2 square, then u3 is my a plus bx3 plus cx3 square. So usually from here we can write it in this form, that is u1, u2 and u3. Then we can write this matrix as 1 x1 x1 square, then 1 x2 x2 square, then 1 x3 x3 square, and then a, b, c, our 3 constants. We can evaluate 3 constants. So if I write this matrix as A, then my ABC is essentially A inverse U1, U2 and U3. So by this way also we can find out the ABC constant, and I think this also we have seen in case of a linear approximation. So now by doing this process you can easily understand that displacement is varying in the node quadratically. In between the element it is quadratically varying. So now in case of a Lagrange polynomial, if I do this, then Lagrange shape functions I can easily write, that is L1 for 3-noded bar element. So that is in general node. So I am not specifying where this node is. Actually node 2 need not be at the middle node or any particular point. So it is valid for any position of node 2. So this is x minus x2, so x1 minus x2 into x minus x3 divided by x1 minus x3. So this is my first shape function or first Lagrange polynomial, and then second is x minus x1, then x2 minus x1, then x minus x3, then x3 minus x2, x2 minus x3, then L3 is similarly x minus x1 by x3 minus x1, and then x minus x2, and then x2 minus x3 minus x2. So now to simplify it in the local coordinate system, let us now do a local system which is this, where x1, instead of general coordinate system, let us first assume that it is on the mid node, is at the midpoint of the element. Then I can just choose any point and derive this shape function. So this is very much just putting the coordinates. So so in the local coordinate system, this is 0 and this is LE by 2 and then this is LE. So now if I do this, and then what I will get is simply just if I put these coordinates here, x2 is LE by 2 and x3 is LE, then I can write the Lagrange polynomial or the shape functions. So I am just writing the shape functions. So that is actually 1 minus x by LE into 1 minus 2x by LE, and then phi 2 is 4x by LE into 1 minus x by LE. So phi 3 is minus x by LE into 1 minus 2x by LE. So if you see, there are three shape functions. These are quadratic shape functions, and then in the same process that we did for the stiffness matrix derivation for the quadratic for the linear element, same process, if I just follow now Kij, the weak form, the elemental stiffness matrix, that is integral 0 to LE, then d phi I dx or dx bar, whatever you say, is a d phi j by dx into dx. If I do this, then I will get the elemental stiffness matrix, which is something like this. So I just don't do the calculations here. You can do the calculations and then you can write the you can check whether the stiffness matrix is correct or not. So this is something like this. If you look carefully, then this is a 3 by 3, it will be 3 by 3 stiffness matrix. Then this is 1, this is minus 8 and this is 7. So this looks like the stiffness matrix for the quadratic element. Now in case of a bar problem, again the force matrix, that is the Fe, if I assume it constant, then Q LE by 6, this is something like this 1 4 1. So LE Fe is essentially this FEI if I write. So this is nothing but integral 0 to LE Q into phi I dx. So if I do that, then if I substitute these shape functions here and integrate over the element, and then I will get the body force vector. Then similarly I will get the this vector. So element the reaction vectors. So basically again the formulation will look like this. Elemental equilibrium is, this is UV, the same equation, only the dimensions will be changed now. So this is my QV. So here it was 2 cross 2 matrix, now it is now 3 cross 3 matrix. This is 3 cross 1 vector, this is 3 cross 1 vector, and this is 3 cross 1 vector. And the rest of the procedure is very simple and same as what we did in the last class. We have to assemble it and we have to assemble the force vector. So if the problem that we discussed in the last class, if I now have the three element, then my 3 quadratic element. So essentially we will have a middle node. So essentially number of node increases. So this becomes 1, 2, 3, 4, 5, 6, 7 nodes. So you see that if I use higher order polynomial, my number of node increases in the discretization. So even though we use the same number of elements, so number of element is 3 but number of node becomes 7, while it was 3 and 4 for the linear case. Now, so global stiffness matrix again, our global stiffness matrix will be 7 by 7 stiffness matrix, and then global displacement vector, which is u, which is also a 7 cross 1 vector, and then global force vector f, body force vector fg, which is also a 7 cross 1, and then q, that is reaction force vector, or qg, whatever you call it, then this is 7 cross 1 vector. And the rest of the procedure, how you will apply the known boundary conditions. Here at this point it is fixed, so u1 is known to us, u1 is 0, and at this point there is a load p, so q1 q7 2 is known to us, which is p, and then the body force is given to this, so which is q. Now this is very similar to what we did in the previous case. So the interesting point here, that the number of element, even though it is same, the number of node increases, by which actually increasing the polynomial order in the approximation. So this is known as the P refinement, or P refinement of the problem. So P refinement. So as you know, any approximating method or any approximate solution, if you increase the order of approximation, at least for elliptic PDEs, the approximation becomes better. Now it is more exact or more closer to the exact solution. So there are two ways to do it. Either you can refine the number of elements. For instance, in case of this bar problem, if I use the more number of element, even still with the linear polynomial, then linear element or two-noded bar element, I can improve the solution. Another way to improve the solution is the increase the polynomial order of the system. That is, instead of a linear variation, I use a quadratic variation or cubic variation of the system. So one important thing here that I wanted to mention, that this node is need not to be at the center of the point. So center of the element, this can be any point, and this you if you know, in case of a crack simulation and other problems, we use something that we don't use a mid-node problem, a mid-node element. We can use at the 1/4 at the this position is 1/4 from the first node. So this kind of something like quarter point element you can think of. So this is known as the P refinement of the problem. So this is what quadratic shape functions, and surely I can use it for cubic element and means then fourth order polynomial. So we'll have 5 nodes and so on. So that is the main issue. But as you refine, as you increase the polynomial order, again the Lagrange polynomial shows so many phenomena like Gibbs phenomena and other things. So those P refinement is generally sometimes problematic. But let us not discuss these issues right now, and then let me go to the eigenvalue problem that we have discussed in the previous lectures. So before that, let me discuss this, that this is the quadratic Lagrange polynomial. So now this is the same thing, we have derived this. Now if you look carefully, that this polynomial is quadratic polynomial. So it is C2 continuous within the inter-element, within the element. That means it is the derivative is twice continuous. So C2 means twice continuous, and but at the inter-element boundary it is C1 continuity. On the similar way, what we have seen in the linear polynomial, it is C1 continuous within the element, but C0 continuous at the inter-element. Now the derivative on the other hand is C1 continuous. Obviously one order reduction will happen because derivative is just lesser order polynomial. So C1 continuous within the element, but inter-element again C0 continuity will expect. So this element is actually globally, if I talk about U variable, field variable U, then this is a C1 element in that sense. So now so this will look like how this polynomial will look like. That's quadratic polynomial. The red one is if you see that it follows the same property that we have discussed in the last class, that is it will be 1 at a Kronecker delta property, at it will be 1 at node 1, and other two nodes it will be 0. So the variation of the function will look like this, and similarly for phi 2 the variation of the function at the mid node it will be 1, and the other nodes it will be 0. And similarly for phi 3, the third node it will be 1, the other two nodes it will be 0. And similarly the derivatives also we can plot. Now again if you look carefully that this polynomial also satisfies the interpolation property, that is quadratic, that is summation of phi x or phi summation of all shape functions, that is phi 1, phi 2, phi 3 at any point within the element should be 1. This will represent the recovery of the constant field. So that means the solution, when we use the approximating solution, because we do not know the exact solution, or probably exact solution is very difficult to obtain. So there it may so happen that some portion of the domain we encounter a constant deformation field or constant axial displacement. So the interpolation property, that is summation of phi I x equals to 1, is just to represent that constant term, so that our approximation is able to predict the constant term. Now the next thing that I plan to discuss in this lecture is this problem. So here we have seen that this is the eigenvalue problem. So this eigenvalue problem is essentially a free vibration problem, so where the steady state solution is periodic, that's the assumption. So in a periodic function I can use the variable separation. So this variable separation, that means ux and e to the power I omega t minus I omega t. E to the power minus I omega t is a periodic function composed of sine and cos. So I assume that this is a steady state solution, so there is a free vibration problem. So that means if I give some initial disturbance to the system, then the system will vibrate and vibrate under its natural frequency. So that's the objective. So the objective essentially find out the natural frequency of the system as well as the mode shapes. So why these frequencies are obtained and mode shapes? Because with this we can find out the solution of the system. So if I know this thing mode shapes, then some that if I know the what is my ux, then I can find out the solution of the system. So in this case, if you look the weak form, then the weak form is pretty similar that what we did in the previous stuff. Only difference is that there will be a mass matrix here. So this quantity will arise in the system because of the inertia term. So here I also discarded the damping term. So you can also include the damping term, but that will just involve the velocity thing. So but here the mass matrix will pop up, and this omega is essentially the natural frequency of the system. So objective is to find out the ux. So with the separation of variable, the time solution and space solution is separated out. So now this in case of a bar problem, simple bar problem, this quantity is 0 because there is no force, because it's a free vibration problem. But a free vibration problem will you need an initial disturbance to start the free vibration problem. Without that it will not happen. So in case of an experimental analysis, if you try to find out mode shapes and natural frequencies, you have to initially disturb the system, then you have to allow it to go to the free vibration or steady state solution. We are interested in steady state solution. So the weak form is this will generate your standard stiffness matrix. Only differences, in place of a displacement, it is just a mode shape, and here it will be your mass matrix. So we'll derive mass matrix, how it can be derived, and this term will obviously be 0 because there will be no force acting here. So this, if I just substitute it here, then this quantity will go to 0. So let us now see what happens. So now let us see what happens. So the eigenvalue problem. The objective of the eigenvalue problem here to find out the mode shapes and the natural frequency of the system. Now any bar or any beam or any plate or any other thing, these are the continuous systems. So it has an infinite number of natural frequencies. So in case of the finite element solutions, so any continuous system will have infinite degrees of freedom. So naturally the infinite number of natural frequencies exist, and what is the first natural frequency is what we are concerned about, is the minimum frequency for which it vibrates naturally. So that is the main lookout from a design aspect also. So now in case of a finite element discretization, we cannot discretize infinitely. So naturally the finite number of frequencies will get, and that depends on how many degrees of freedom essentially you are considering within the system. So for instance, the weak form, if I write, the weak form looks like this. This is 0 to L. So D, let us take W as the shift functions, and this is dx, and then A d u dx, and then this is so I can put it, change the sign. So this is minus, so omega square, this is the natural frequency, and then integral 0 to L rho A. Rho is the mass density, A is the area, and then W u dx. So this is my weak form. Now similar to the previous case, this will give me a stiffness matrix which is Ke into my u vector, ue vector element wise. So, this is a mode shape vector. So, now this will give me again omega square. So, this will give me a mass matrix. So, this is my mass matrix and this will give me a so it contains u. So, this will give me a mode shape vector. So, this becomes 0. So, now if I write it, this is Ke minus omega square m e. So, this is my eigenvalue problem. Here if you notice that this is my unknown and this is my unknown. So, now here this omega is the natural frequency and u is the mode shape. So, this is standard eigenvalue problem which is a ax equals to lambda bx, something like this. So, this is generalized eigenvalue problem. So, how we solve eigenvalue problem, that we have discussed already. So, that is the take the determinant of it and make it 0. So, characteristics polynomial, I make it 0. So, I will get the number of roots based on the order of the characteristics polynomial. So, similarly here in case of a finite element discretization, I will get the number of roots based on the number of nodal points or number of discretization I consider in the system. So, now the procedure is very simple. How to find out this ME? We know for linear element, we know what is my Ke. So, and we have to find out the ME. So, the MEIJ, if I write it from here, so that is essentially 0 to LE rho A, then W is my weight functions which I am considering phi I, and then U I am considering phi j. So, this is my MIJ. Now, if I substitute my phi 1 and phi j is 1 minus x by LE and phi 2 is x by LE, then my system, if I just substitute it, so for instance M11, if I just substitute it, then it will look like 1 minus x by, you can well use the bar quantity if you want, because it is in local coordinate system. So, this is LE and then 1 minus x bar LE. So, if you do this exercise, then you will get the mass matrix associated with this. So, this will is rho A by rho A LE by 3, I think. Okay. So, now if I do it for M12, M21 and M22, then I will get the mass matrix for the linear bar element, which looks like this. So, essentially this is rho A LE by 6 into 2 1 1 2. So, this is my consistent mass matrix. So, sometimes we use nodal lumping of the mass, that is in case of a 2-node element, half of the mass is lumped on an one node and half of the mass is lumped on the other node. So, this will lead to a diagonal mass matrix. Sometimes we also prefer the diagonal mass matrix when we simulate the your dynamics problem or the transient problem, which involves time domain solution. So, this is a frequency domain solution. So, sometimes we prefer lumped mass system. So, that is purely due to the numerical problem. Now, this is consistent mass matrix. So, how mass is distributed along the degrees of freedom. So now if I know my mass matrix, then the rest of the procedure is very simple, the standard assembling procedure. So now my kg, I will get the global stiffness matrix, then I will get my omega squared. Now omega is the eigenvalue here. Now similarly I will get the global mass matrix, and this is multiplied by the global vector, which is this u, the mode shape vector. So naturally the eigenvectors for this, if I solve this eigenvalue, so this is a homogeneous system, so naturally this equals to 0 and product of these two is 0, so either this equals to 0 or this equals to 0. So this equals to 0 is a trivial solution, which we don't want, because u equals to 0 is the trivial solution. So non-trivial solution will only arise if determinant of this quantity is 0. So naturally this det of this quantity, determinant of this quantity, will lead to my characteristics polynomial, and then I can find out based on the number of degrees of freedom I consider, I